chapter 7, which is the smaller, I'm going to put this on, smaller set of notes. Okay, yeah, so texture map. Anybody heard of texture mapping before? Yeah, so sort of, so I would take it the majority of you don't know what it is. Okay, well, it's something which is quite common in graphics, particularly in computer games. So this is something which is sort of propped up in the 90s, and it just makes, it's a way of making our virtual worlds a lot more realistic. Polygon shapes. Okay, so this morning in the first lecture, we'll be looking at the mathematics behind it, how we apply texture mapping. In the second lecture, I'll be looking at ways to improve texture mapping, and also we'll have a look at some a past paper question on the subject. Okay, so essentially, what is texture mapping? Well, it's a process of mapping a two-dimensional image onto a three-dimensional polygon. So we have polygons in our world space. You're quite used to that now with all the assignments you've done. So our world space is made up of polygons. A 2D image, let's say we've got a photograph. Let's say we take a photograph of something. Let's say we take a photograph of a brick wall, and we have a polygon in the world space which represents that brick wall. What we could do is literally paste that image onto the polygon. So rather than having to use lots and lots of polygons to model each brick, and therefore we color them in using our filling methods, what we can do is we can use a big polygon to represent lots of bricks, take a photograph of some bricks and paste it on. That's essentially what we're doing. It's applying an image to a polygon. The image that is mapped onto the polygon is called a texture. Okay, the image can be anything as long as it's what we call a bitmap, as long as it's like a raster. So photographs, it could be patterns, could be anything. A texture has to have. Okay, in our texture map, so if there's a pixel in that texture, the way which we can differentiate our raster array pixels on our texture map. The pixels on our raster array is displayed on a screen, determined by the colors of the textiles. From space back to I've got this 109 in the notes. So you're well versed with the idea of world space. That's your 3D space, which is aligned or sometimes aligned to the viewer. Okay, you have your screen space, so we project it using perspective projection, so that then we could represent the screen space on a raster. I'm going to introduce another type of space, and this is called the texture space. Okay, so far I think we got object space, where your objects like the houses and buildings and things like that are defined. World space is your virtual world. Screen space is then your virtual world projected onto the viewing plane. Okay, so your texture space is an addition to that. And this is where your texture exists. So what we want to do is, here we've got a texture of a smiley face. We want to be able to paste that smiley face onto some polygon in the world space. That polygon in the world space onto our projection plane, we should see that smiley face. But we can't project a bitmap. Okay, we can't project a texture. We can only project vectors, because that's when we look at the or when we looked at perspective projection. Okay, it was all to do with vectors. Now a texture is what we call a bitmap. It's made up of pixels, like a raster. So how do we go from the screen space to the texture space is our problem. Okay, texture space. As I mentioned, a texture space is simply the space in which the texture exists. Okay, it's 2D. Okay, well, an image, a photograph is only going to be 2D. It's got no third depth dimension. So it's a 2D space, and we refer to the horizontal and vertical coordinates as u and v, simply just to avoid confusion with x and y. So when I mention u and v, I'm talking about texture space coordinates. And u and v are always in the range 0 to 1. Okay, so nothing exists outside of 0 to 1. Okay, and a texture must fill the texture space. So if you were to take a photograph, the bottom left corner of the photograph would correspond to texture space coordinate 0, 0, and the top right corner would correspond to 1, 1. Okay, so anywhere in between, you're somewhere in the photograph. So your texture space doesn't exist outside of that range. The coordinates of a textile, and I've used big V, a big U, and big V to denote coordinates. So it's quite important to differentiate, or to sort of realize that little u and little v are in the range 0 to 1. Big U and big V, these have got to be textile coordinates. So like pixels, okay, textiles are whole discrete entities. So our textile coordinates have to be in the range 1 to the number of textiles in our image. So if it's along the horizontal direction, okay, we go from 1 to mx. So if mx is the number of textiles in the horizontal direction, my is the number of textiles in the vertical direction, okay, we have to do a scaling. Okay, so the u and v are scaled. Mx times u, okay, so that's a number between 0 and 1 times by the number of textiles, add 1 to it. And these brackets, okay, as you can see, they're not actually brackets. I've got no sort of roof on the brackets. Okay, these mean floor. So these mean round this number down to the nearest integer below. Okay, so that's what we call a floor function.
So it's like 3.8.
Exactly, yeah. So if you had the number 3.8, that would go to 3. So you round to the first integer down. So this is how we scale our textile coordinates. So u and v will therefore be integers. Unfortunately, we do have a problem that when u or v is equal to 0, using this scaling, we'll get big U equals 0. We can't have a 0 pixel. Okay, pixels are natural. Well, we number pixels using natural numbers 1, 2, 3. We don't have a 0th pixel. And the same when u equals 1. When u equals 1, big U will equal mx plus 1, which is, there's no mx plus 1. It's outside of the range of our texture. So a little bit of a fudge, a little bit of a sort of something we just do to make it work, is we check to ensure that u and v are greater than 0 and less than 1. If they're not, we just add something to it or take something away just to make sure they're in that range. Okay, so here's a little MATLAB function. All this function does is it takes in little u and little v as the texture space coordinates, and it also takes in mx and my as the size of your texture. First thing it does is ensure that u and v are in the range 0 to 1. All we do is an if statement. And what I've got here is if u is less than or equal to 1 millionth, I just chose a small number. Okay, I could have chose 1,000th, I could have chosen 1,000,000th, this is sort of some small number. If it is smaller, I just make sure u is equal to that really small number. This sort of nudges it just above 0. So when we do the floor, add 1 to it, floor it, it will be 1. And the same thing is if u is greater than 1 minus a millionth, just make sure it's equal to 1 minus a millionth. So this is kind of a fudge. It just makes sure that u is greater than 0 and u is less than 1. And here, do you want to take that one? And here we have the floor. Okay, as you can see, the MATLAB command is obviously quite sensibly named. So floor mx times u plus 1, and that gives us big U and big V. Okay, so these calculate the coordinates of the textile, which corresponds to little u, little v. Okay, so now we're going to discuss how we go about applying the texture map. So we have our texture in the texture space. So remember, this range is u is 0 to 1. This range here is also 0 to 1 in the v direction. This is our screen space. So what I've done here is I've deliberately rotated the polygon just so it's not parallel to the x and y axes. Okay, so these are xs and ys, so these are screen space coordinates. And from our scanline method, we know that we take horizontal rows of pixels, and with scanline filling, we filled in a whole row of horizontal pixels. Well, we do similar with texture mapping. So what we have here is a scanline. Okay, this is on my screen space, and PL and PR are left and right scan extremer. So this is the edge of the polygon, the left edge, and that's the right edge of the polygon there on the scan line. Now this dotted line here, which is a scan line across the polygon, okay, the colors of the pixels on the scan line correspond to this dotted line on the texture. Okay, so as you can see, we go through the sort of top portion of the eye around there, so that corresponds to that bit there. So we need to map our PL coordinate to QL. Okay, so that's QL is the scan extremer on the texture space corresponding to the scan extremer in the screen space, and the same with QR. So what we have is we have a polygon defined by P1, P2, P3, P4. Doesn't matter where they are. Okay, but what we also make sure we do is in the texture we have corresponding corners of our texture map. Okay, so if P1 is the bottom left corner of our polygon, that corresponds to Q1, which is at 0, 0 in the texture space. P2, bottom right corner, will correspond to Q2, which is at 1, 0 in the texture space. And similar for Q3, corresponds to P3, Q4 corresponds to P4. Okay, so we're going to have to calculate, every time we go down a scan line, we're going to have to calculate PL and PR, and then calculate pixels, or textiles rather, along that dashed line. Okay, so that's how we apply it. So this is sort of really repeating what I've just said. So the vertices of the polygon P correspond with vertices in the texture space Q. Any transformation, so any rotation or translation or reflection that we do in the world space needs to be accounted for by the texture mapping. And that's pretty much automatically done. As long as, for example, Q1 corresponds to P1, Q2 corresponds to P2, etc. So any sort of rotational which we apply to this polygon here, the texture mapping should take it into account. We use the scanline method. So the scan extreme of PL, in this case, is calculated by interpolating between P4 and P1. Okay. So as the scan line's up here, PL is between P4 and P1. If the scan line was down here, it'll be between P1 and P2. Okay, so depending on where the scan line is, what vertices it's between is what we interpolate between, and similar for PR. Okay, the corresponding scan extreme of points QL and QR are calculated by interpolating between Q4 and Q1 and Q4 and Q3 respectively. That depends on what edge of the polygon in the screen space that your scan line is on. And the pixels between PL and PR take on the same color as the textiles between QL and QR. So it's actually quite a simple idea. Okay, a row on your screen is equal to some line on your texture. Okay, so this is where we have to do a bit of linear interpolation. So your vertex coordinates are scaled to the size of the raster. So you have some screen space coordinates. Remember, they're between -1 and +1. Okay, remember when we did clipping, we clipped to a unit cube. So all your coordinates are between -1 and +1, and therefore we have to scale it. So this is also a sort of a tip for your raster assignment. So the scaling is done, you add 1 to your screen coordinate, multiplied by the number of pixels in your screen, divided by the size of your screen space. So -1 to +1 is 2. So that's the scaling. The max 1 just ensures that if this is less than 1, we don't have 0, we have a whole number, coordinate 1, and similar in the y direction. Okay. To start with, the scan extremer, PL and PR, are initialized to the largest y coordinate. So in this case, if we have a look at our screen space, the largest y coordinate, or the vertex of the largest y coordinate, is P4. So in this case, we use P4. So PL and PR are both equal to P4 to start with. And what we do is we go down each horizontal row, so exactly the same as the scanline method. So the y coordinate of the next scan line is simply y coordinate, the current scan line, -1. So we subtract 1 from the y coordinate. If we look at the left scanline coordinate, well, the y coordinate's already been calculated, but the x coordinate, we're going to have different ones for the left and right scan extremer. Okay, the left scan extremer is interpolated between P4 and P1. So here we have the left edge. So this PL here is between P4 and P1. So I'm going to have to interpolate or linear interpolate between these two vertices. Okay, so use linear interpolation. This is just a form. This is just from straightforward interpolation. So we have your x coordinate at the P4 point minus, okay, so y4 minus y is this distance. So that's y4, that's y. So the vertical distance between the top vertex and the scan line. And if we divide that by the vertical distance between P4 and P1, so that gives us how far down as a proportion is this scan line along that edge. Okay, and then that's multiplied by the horizontal distance between P4 and P1. Well, we can simplify that a bit, because since your y coordinate is equal to y, well, your first y coordinate is equal to y4 minus 1. If we substitute y4 minus 1 in place of y here, we simplify it. So we have x4 minus x1 divided by y4 minus y1. Okay, and that makes it easy. That fraction is going to be constant because it's a straight line. That's a gradient. So the gradient is constant along the polygon edge. So the fraction can be pre-calculated. So I've called it delta XL. So that's a change in x on the left side of our polygon. So our next left coordinate of the scan extremer is equal to the current left coordinate minus the change, and that's constant. Your first XL is just equal to the top P4. Okay. So as you go down the scan lines, your XL and XR will be calculated just by subtracting delta XL and delta XR from it. And essentially, this is the width of left edge divided by the height of left edge. Okay, so that's calculating your scan extremer. That's your PL and PR. Okay, it's slightly more complicated when we look at the scan extremer in the texture space. what we have here on the right is your polygon. Okay, so this was our P4, there's our P1. So this left scan extremer is going to start off up here, and it's as we go through the scan lines, it's going to end up down here, and then it's going to change to the bottom edge. So the corresponding one in the texture space is going to start off at Q4, which corresponds to P4, and as in the screen space, the left scan extremer goes between P4 and P1. This one is going to trace the left side of the texture between Q4 down to Q1. So this UL VL will just simply go down this left-hand boundary. When the scan line gets to about here, so underneath P1, we're going to change, and the left scan extremer is going to go between P1 and P2. Well, therefore, that's going to be between Q1 and Q2. And similar for the right one. Okay, so this starts off at this point, and you're going to have diagonal lines. Each scan extremer is just going to start off at the top and make its way down to the bottom. That corresponds to P4 all the way down to P2. Okay, so that's what we're going to have to do. So if we trace down the left edge, VL is going to change. UL is always going to be 0 because we're on the left edge. Okay, so VL should go between V4 and V1, which will be 1 and 0. In the same span, that Y goes between Y4 and Y1. So therefore, our change in the V coordinate is V4 minus V1 divided by Y4 minus Y1. So as you go down 1 pixel in the screen space, you go down that change in the texture space. And I've also got similar for UL. But when we're on the left edge, UL, U4 and U1 are both 0. So this is going to be therefore 0. But when we get to the bottom, when we're going across this span, okay, delta V becomes 0, and then delta U is some non-zero number. Okay, and as PL moves to the next scan line, you just subtract delta UL from the current UL. And similar for UR and VR. So you're starting at Q4, you're starting at the top left corner, and then you're changing it depending on your scan line in the screen space. Okay, almost finished. Now what we have to do is go across your scan line. Okay, so this is across this dashed line here. Okay, so we start at the left scan line. So we initialize U and V to be UL and VL. For every pixel we move across on the screen space, we're going to change the U and V coordinates by adding delta U and delta V. Okay, so we need to go across this scan line in the same span as the width of this dashed line in the texture space. Okay, so what we do is we take the difference in the U coordinates divided by the difference in the scan line width in the screen space, and we do the same for the V coordinates. So there's quite a lot of work. There's quite a lot of interpolation essentially. So we've got to go from screen space to texture space. Once we've got U and V, we then have to calculate textile coordinates and then apply the color. Okay, so there's the output. I'm going to show you this. Actually, hopefully it's downloaded by now. Yeah. So if I'm going to it'll open up. Good. Okay, so this is a program I wrote just to apply the texture map. Okay, so I initialize a 400 by 300 raster array. Okay, what I've done here is I've multiplied it by 255. Now that may seem odd, but the reason I've done it is I'm using a double precision array. For some reason, it didn't work with standard precision. When I mean double precision, I mean I'm increasing the amount of memory I have for each number, essentially. So the 255 means we're going to go, our range goes from 0 to 255. So that's equivalent of 8 to the power 3, 2 to the power 8. Yes, 2 to the power 8. So it's true color. So we go from 255, 0 to 255. And when I actually plot it, which is down here, yes, I'm using double position. So for some reason, I tried it with single position and it didn't work. So if that's a bit confusing, just to make it work. Okay, I've loaded in a texture map from a photograph. Okay, and here what I've done here is I've just projected it using perspective projection, and I've done a bit of rotation as well. Okay, essentially, this is the bit that applies the texture map. Okay, so I've written a function that takes in the raster, takes in the texture, takes in your P vertices, and then returns the raster, which is then plotted to the screen. Okay, so if I just show you the texture map function. Okay, so I'll talk you through this. Texture vertices, these are your U and V coordinates for your Q1, Q2, Q3, Q4. So they're in the range 0 to 1. And calculate the size of the texture. So MY and MX are just the number of pixels or textiles in your texture map. This tilde here means I'm not interested in what the third dimension is. You could scrap it if you want. I'm telling MATLAB I don't really care what that third dimension is. Okay, first convert screen space coordinates to pixel coordinates. So we have to scale it. And then we loop through the scan lines. So Y max is what's the maximum value of the Y coordinate, and Y min is the minimum. So I start at the top. -1 means I'm subtracting 1 from Y each time, and I should end up at Y min. Okay, now we got this sort of complicated for loop. And what this does is it determines where our scan extremer, or which vertices our scan extremer is between. And I've called them LT, RT, meaning left top, right top, and LB, RB, meaning left bottom, right bottom. So J and I are just, okay, which two vertices are these between? So to start with, left top and right top would be 4 and 1, because it's between P4 and P1. Okay, down here, this is where I calculate XL, UL, and VL. So I calculate what's the change in the X on the left edge, change in the U for the left edge, change in V for the left edge, and do the same for the right edge, same thing. Okay, and finally loop across scan line, calculate the textile coordinates corresponding to U and V, and then apply them. Okay, so you can see that's the result. So on the left is a picture of my cat, which is the photograph, and on the right is the polygon which I've applied. So notice I've sort of rotated that polygon slightly, and the one on the right is actually a raster array. It's 400 by 300. So I can show you that actually working on MATLAB. If I go back to here, hopefully it will work. Fingers crossed. Change folder. Oh, and I'm showing you something which I want to show you in a minute, but go back to the code. So try it again. There we go. So as you can see, it's rotating. So any rotation that I apply to the polygon automatically applies in the texture map. Okay, so that's good news. Okay, the other thing I wanted to show you is, okay, that appears to work. So I've rotated that polygon about the about the Z-axis, and it appears to work. We have a bit of a problem when we actually rotate it around the Y-axis. So in this case, the left edge of the polygon should be closer to the viewer than the right edge. So using perspective projection, this end looks bigger. But what happens is it skews the image. So I don't know, well, obviously I know the cat better than you do. She's not this fat. Okay, so this has made her look really fat on this end. So I'll show you that animated. Okay, can you see there's something sort of not quite right there? It sort of doesn't look, realistic. I'll run that again just to show you a final time. Quite hard to explain. It's what we call skewing. Okay, as you're looking at that, you don't believe that that texture's been applied to that image very well. It's easier to see if I have an image of an X. So what I'm going to do is I'm going to replace the texture with a texture which is of an X. There you are. So that is an X, and you can see as it sort of gets around, curves round, the lines which join the diagonals should be straight or should appear straight. So they're getting skewed. So even though after we did all that work, all that interpolation, it's still not quite right. And that's so that's a texture on the left, which is just a 100 by 100 texture, and all I've done is I've done the diagonal elements in white. And when you apply it using what we call a linear texture map, okay, it looks skewed. So those lines on the right-hand side, they should be straight. They should appear straight, but they're actually curved. So we've got a problem. And that's a problem which we're going to look to rectify in the second lecture. Okay, I appreciate a lot of this is kind of dry. It's kind of, okay, we have to interpolate this, interpolate that. But it's a very neat bit of application of mathematics. Okay, before, I mean, doing some research on texture mapping, people have got all sorts of weird and wonderful ways of doing things using complicated vector mathematics. It's not that complicated. As long as your corners of your polygon correspond to the corners in the texture space, it's just a matter of interpolating, and that's it. Okay, so we're sort of finished slightly early there. So let you have a coffee or something, and I'll see you again at 11. Sorry. Oh, sorry. Just got to.